Hey everyone, welcome back. In this video, we are going to discuss or talk about a new concept in set theory and is known by the name of relation. You know what? We encounter many relations in our day to day life. For example, you can see these three examples that you frequently use in your day to day life. For example, Iqbal is son of Akram, Junaid is friend of Sujil, Mehak is wife of A. Okay. In particular, in mathematics, we encounter several relations such as line L1 is parallel to line L2, line L1 is perpendicular to line L2, the real number x is less than the real number y, and etc. In these examples, it is clear that a relation involves two objects. Obviously, here I am stating some fact, and the fact is Iqbal is son of Akram. Is son of is a kind of relation that relates Iqbal with Akram or Akram with Iqbal. So as you can see yourself in all of these examples, in these non-mathematical examples and also in these mathematical examples, as you can see, a relation involves two objects. It connects two objects, two different objects, or maybe the same objects. Now these are the examples of relations. These three examples are from non-mathematical area or from everyday life, which are not mathematical, and these are from are well-known relations from mathematics that you may be knowing already. The question is, how can we make this concept, the concept of relation, more precise? Is it possible to give a more general definition of a relation? Question number second. And if so, how we define a relation? The answer is yes, it is possible to give a more general definition of a relation, and we define a relation in terms of set itself. So how we define a relation in terms of set? Here we go. This definition is the formal definition of a relation, and this is set theoretic definition of a relation. Now let's see what this definition tells us. It reads, given two non-empty sets A and B. Now I have used non-empty sets, so A and B are not allowed to be empty. Given two non-empty sets A and B, then a relation R from the set A to the set B is a subset of A cross B. That is, if A and B are both non-empty, then R is the subset of A cross B, and it defines a relation from set A to the set B. Once again, this definition tells me that a relation from a non-empty set A to another non-empty set B is nothing but a subset of A cross B. So a relation is actually a set and nothing more than that. So let's do the postmortem of this definition. After doing the postmortem, I have some observations regarding this definition, and here these are. A relation is basically fundamentally a set. And what kind of elements a relation contains? It contains ordered pairs. The nature of a relation from a set A to a set B is that its elements are ordered pairs. Note number second, a relation from A to B is a subset of A cross B. That is, R is a subset of A cross B. Point number third says, relation has a direction. For example, I have this non-mathematical relation, A is son of B. Now, A is related to B by this relation. Now, if you reverse this, what will be the relation of B with respect to A? Obviously, B is the father of A. And we know he is son of and is father of. These two relations are quite different. That is why when you talk of a relation, you talk of it specifying the sets, from which set the relation starts and at which set it ends. So in general, a relation from the set A to the set B is not the same as the relation from B to A. Domain of relation. Given a relation R from A to B, that is R is given by this, R is a relation, and of course it is a relation from A to B, and it means that it will be a subset of A cross B. Then the set D defined by this, the set of all A such that A comma B belongs to R, is called the domain of R. Domain of a relation R is simply the set of all the first entries of the ordered pairs, which are the elements of the relation R. This definition of a domain of a relation simply tells me that domain of a relation is nothing but the set of all the first entries or first entries of the ordered pairs belonging to the relation R. Similarly, R defined by this set is called the range of R. Range of R is nothing but the set of all the second entries in the ordered pairs belonging to the relation R. And you should note this domain of a relation is the subset of the set A, and range is the subset of the set B. Point number 5. Since phi is the subset of A, where A being an arbitrary set, it means that A is any set. And we know phi from earlier set theory, we know phi is the subset of every set. And this statement is true vacuously. Now, if phi is the subset of every set, it means that phi is also going to be subset of A cross B. Now, apply the definition of, because phi is now the subset of A cross B, it implies that phi is also a relation from A to B. Now, if it is a relation, we have a name for it, and is known as the empty or the trivial relation. And we also know that every set S is a subset of itself. So, if every set is subset of itself, it means that A cross B is also a subset of A cross B. Now, apply the definition of a relation, you will get that A cross B is also a relation and is known as the universal relation. Point number 6, it says me that if A comma B, the ordered pair A comma B, is an element of R or belongs to the relation R, which is of course a subset of A cross B, we say B is image of A under R and A is known pre-image of B. If A is related to B through the relation R, B is called image of A under R and A is called pre-image of B under R. Okay. Now, what I defined the relation from a set A to another set B and didn't mention that whether A and B are equal or not. It means that this condition of being equal or different is relaxed in the definition. So what will happen if I replace the set B by the set A itself? Now, if we replace the set B in the relation from A to B, the relation will become from A to itself or from A to A. Such a relation is known as the relation on the set A. A relation on a set A is nothing but a relation from A to A. Thanks a lot.